Hello, welcome to the class of Advanced Stats and Econometrics. In today's lecture, we are going to discuss asset price volatility, and we are going to use ARCH and GARCH model and so how they can be useful when we have asset price volatility. So, first of all, what is a volatility clustering? Volatility clustering are basically periods of turbulence in which prices show wide swings and periods of tranquility in which there is relatively calm, which means there are periods in which there is large change in prices and then there are periods in which there are minor changes in the price. Financial time series often exhibit the phenomena volatility clustering. This results in correlation in error variance over time. Use autoregressive conditional heteroscedastic arch models to take into account such correlation or time varying volatility. Arch model. This model shows that conditional on the information available up to time period t minus 1, the value of the random variable y is a function of the variable x. That is y subscript t given information available at time t minus 1 is denoted as I. This is equal to alpha plus beta times xt plus ut. We assume that given the information available up to time t minus 1, the error term is independently and identically normally distributed with mean 0 and variance sigma squared t. Heteroscedastic variance. Notice here subscript t. If it is homoscedastic variance, then there is no need for subscript t. Sigma square will be the notation. Now here the variance is different. That's why time period t is mentioned. So ut is heteroscedastic. Given information available at time t minus 1, ut is a IID, that is identically and independently distributed normal distribution with mean 0 and variance sigma squared t. T is written because it is time dependent variance, it is not constant, it is heteroscedastic. Assume that the error variance at time t is equal to some constant plus a constant multiplied by the squared error in the previous time period. So it is equal to sigma squared t. Then you have lambda naught plus lambda 1 times u square t minus 1, where lambda 1 is between 0 and 1. Arch 1 model include only one lag squared value of the error term. That's why you have in the parenthesis 1 because it only include one lagged square term of the error term. Arch P model has P lagged square error term and it can be written as sigma square T is equal to a function of ut minus 1 ut minus 2 till u square t minus 1 u square t minus 2 till u square t minus p. So you have lambda naught plus lambda 1 times u square t minus 1 plus lambda 2 times u square t minus 2 till lambda p times u square t minus p. So p period lag are there. If there is an arch effect, it can be tested by the statistical significance of the estimated coefficients. If they are significantly different from 0, we can conclude that there is an arch effect. Estimation of the arch model. The least square approach. Once we obtain the square error terms from the chosen model, we can estimate the arch model by the usual least square method. A Kaiki or Schwarz information criteria can determine the number of lag terms to include. Choose the model that gives the lowest value on the basis of these criteria. So if in one model the value is lower, it is preferred, and we are going to select a model that gives lowest value on the basis of these criteria. Then maximum likelihood approach. An advantage of maximum likelihood or ML method is that we can estimate the mean and variance function simultaneously. The mathematical detail of the ML methods are somewhat involved, but statistical packages such as Stata and eViews have built-in routines to estimate arch model. So Stata and eViews are popular software used for econometrics, and eViews is specially used for time series. Drawback of the arch model. The arch model requires estimation of the coefficient of p autoregressive terms, which can consume several degrees of freedom. This is one of the severe limitation of the model. If P is large, we lose a lot of degree of freedom. It is often difficult to interpret all the coefficients, especially if some of them are negative. The OLS estimating process does not lend itself to estimate the mean and variance functions simultaneously. Therefore, the literature suggests that arch model higher than arch P is better estimated by the GARCH model, and GARCH model are generalized autoregressive conditional heteroscedastic models. So when we write the GARCH model in its simplest form, the variance equation in the GARCH model is modified as follows. Sigma square T is equal to lambda naught plus lambda 1 u square t minus 1 plus lambda 2 sigma square t minus 1. Notice this is known as GARCH 1 model because it is involving 1 lag period for u square t terms and 1 lag for sigma square t. That's why we only have t minus 1 and t minus 1. Had it been u square t minus 2 and sigma square t minus 2 terms also, then it would become GARCH 2 model. So arch P model is equivalent to GARCH 1 as P increases. Note that in the arch P we have to estimate P plus 1 coefficient, whereas in the GARCH 1 model given in we have to estimate only 3 coefficients, that are lambda naught, lambda 1 and lambda 2. GARCH 1 model can be generalized to the GARCH PQ model in with the P lagged square error term and Q lagged conditional variance terms. But in practice, GARCH 1 has proved useful to model returns on financial assets. So usually GARCH 1 model is sufficient. It has proven itself. So we begin with GARCH 1 model unless we have some other consideration which provide a better model by going for a higher lag period P and Q, higher value of P and Q. So how can we further extend the ARCH model? One is GARCH M model, that means mean, GARCH in mean. Explicitly include a risk factor, the conditional variance in the original regression. If we have this YT written as a function of xt and sigma square t, so this yt is equal to alpha plus beta times xt plus gamma times sigma square t plus ut. This is called GARCH M11 model, because here you will see that furthermore we can extend the arch and GARCH model along various lines, that is arch, sarch, tarch, narch, narch k, e arch. These are all variants of the arch and GARCH model. But most often we prefer GARCH model because this is most frequently and most widely used model in the financial asset volatility. So every time you see a volatility model, you need to estimate it. You prefer GARCH model. If you see that there are variation in the model itself, if you want to bring some variation, then you can modify the model, you can extend it along different lines, and these are the different extension of the GARCH model, an arch model. And the reference for all this is a book called Econometrics by Example, second edition. Publisher is Palgrave Macmillan. and the author of the book is Damodar Gujarati. And that's it for today's lecture. Thanks.